Earlier in this section, we took what I would call a high-level view of the Ethernet header and trailer, and by that I mean we recognized where they were. The Ethernet header is ahead of the data, the trailer is trailing the data, but we need to know a little more detail than that. And let's start with a detailed look at the Ethernet header, leading off with the somewhat formally named preamble, followed by the somewhat complicated sounding start frame delimiter. But it is not complicated at all. You'll see what it's about in just a moment. That's followed by our layer 2 addresses. First the destination MAC address and then the source MAC address. And then finally that header ends with a protocol type field. Let's talk about each one of those fields for just a moment. The preamble is a 7-byte set of alternating ones and zeros. That's all it is. 10, 10, 10, 10, repeated 7 times. It's used for clock synchronization. And that's all the detail we're going to go into here because that's a real nuts and bolts thing. It's way beyond the scope of the exam, but that's what you need to know about the preamble. Now that SFD, boy, that start frame delimiter, that sounds really complicated, but it's not. It's a 1-byte field and it's almost set identically to any of the bytes from the preamble, except it ends in a 1. It's 10101011, and the SFD's sole purpose is to indicate the preamble is ending and the destination MAC address is about to follow. And it does. There's the destination MAC address, the frame's destination. Much more about that coming up in the next couple of sections, as with the source MAC address. Now the protocol type it indicates the protocol type. What else are you going to say about it? In our network, that'll be IP version 4 for almost all of the course, and then in the IP version 6 section, of course, that would reflect IPv6. And now for a detailed look at the Ethernet trailer. And there it is, the frame check sequence FCS, that is it. But it's a very important it. And there's also some terminology here. I want to draw a clear line between a couple of terms here so we don't get them mixed up on exam day. Now the FCS might not look like a whole lot, it's just sitting there at the end of the Ethernet frame, but it is a very important error detection operation. Now the sender arrives at a numeric value by running what we call a cyclic redundancy check, a CRC. You can also say cyclic if you want to. Just call it the CRC. It's a complex mathematical operation, and it's run against the data contained in the frame. And the numeric value that is a result of the CRC is placed into the FCS, and the frame is then sent. The recipient of the frame will run the exact same CRC against the exact same data, the incoming frame's data, and it's going to compare the answer to that contained in the incoming CRC. Now, if those compared values are the same, the frame is non-corrupt, pigeons are released, life goes on. But if they're not the same, then something has happened to that frame and it's then considered corrupt. But there is no specific notification sent back to the sender that frame needs to be resent. The frame will be thrown overboard. It'll be discarded. It's no good. But the recipient doesn't send an explicit message back to the sender saying, hey, you need to retransmit that frame. Now we have protocols that might do that for us that we're going to be introduced to later, but by itself, the FCS is strictly for error detection, not error correction. Two very different things, because you're going to run into network services and protocols and situations where there's error detection, finding out about a problem, but that service or protocol doesn't do anything about it. Error correction is finding the problem and actually doing something about it. So again, the FCS strictly for error detection. Now, a quick and final word on cables. We spent plenty of time on the wires in the cable and how the wires run end-to-end in different cables. But the wires and the cabling and the wrapping, in the one case, in shielded twisted pair, we need a little something to top off the cable at each end, don't we? Yeah, something like this. This is an RJ45 connector, and it is used to terminate the wiring at the end of the cable in hopefully a nice, neat fashion. And this is really the most common type of UTP connector you're going to run into in the field. Now that little plastic tab, I want to show that to you again. Sometimes that is protected by a very hard plastic shell, and you'll see pictures of them that way. It's the same connector, works the same way. You can break a blood vessel in your thumb trying to push in some of those things, so you can push the tab in enough to put it into a switch or whatever port you need to put it into. And others just have a little protective shield at the end of the tab just to try to prevent it from breaking. You can still use a cable, a connector with a broken tab, but you might not be able to get it back out and it might not see correctly to begin with. So I don't recommend it if that tab is broken. You just put the connector into the appropriate port, you push in gently until you hear or feel a little click, because sometimes in a network closet with all kinds of routers and switches around, it's hard to hear that little click, and you're all set. And it just ends up looking just like that. So just a little extra word there about cables. We talk so much about the wires, but we tend to ignore the connector at the end of it. RJ45 connectors are not the only connectors you'll run into in the field, but by far the most popular, and you'll be using those in a lot of Ethernet and fast Ethernet ports. That is it for cables, and we are nearing the part of the course where we start diving into live labs. We're going to start the next section with a little bit of a history lesson on hubs and repeaters. It'll show you how we got to switches, and then after that we are going to look at some switch theory and plenty of switch labs. So take a deep breath, and I'll see you in the next section of the course.